Greetings, fellow grade 11s. It's Mr. Shatra again. Welcome to Back to Basics. Now, look, what we are going to be looking at today, basically, we are going to be looking at a past paper of 2018, right? So this is November 2018, physical sciences. Right now, let's see. So now in this question, they say in an experiment, a learner added 1.5 grams of sodium carbonate to hydrochloric acid. Now, the volume, or rather a volume of 306 centimeter cube of carbon dioxide gas formed and collected under standardized, or rather standard pressure at a room temperature. Now, take the molar volume at room temperature as your 24.45. Now let's see in terms of what is it that we can do now firstly here. Now the first question require us to do what. Now it require us to basically now define what is 1 mole of a substance, right? So now so 1 mole of a substance basically can be defined as the amount of substance having the same amount of particles as your atoms of your carbon 12, right? So which means we are saying now 1 mole, 1 mole is the amount of substance. It's going to be the amount of a substance having the same. So let's see, having the same particles as the ones of a carbon 12, having the same particles as are in atoms of carbon 12, in atoms of carbon 12, right? Carbon 12, rather as of 12 grams of carbon 12. So basically that, so please ensure that whenever they require you to do a definition, ensure that you look, or rather you check the one on your exam guideline, because that's the one that it is mostly preferable, right? So please be in a position that you use the one in your exam guideline. Now, secondly, now 6.1.2, let's see in terms of what 6.1.2 require us to do. They say we need to balance the equation for the reaction. Now let's start here. Now let's copy this equation again. You have Na, you have CO3, which is in a solid state, plus your hydrochloric acid, which is your aqueous solution, which forms your NaCl, which is same as your aqueous, plus your H2O, and plus your CO2, right? So basically now this is going to be the equation that is given. Now, how do we then balance this? Now, you know, the best way of balancing this, I usually prefer that now you calculate in terms of how many atoms of a certain compound or element do you have on the side, and compare them to the ones that you have on the other side. Now, let's start here. Now, if you can check, look, you have your Na here, you have one Na, which is your sodium. Look, this is Na2. So basically, which means you have 2 elements, or rather 2 atoms of your sodium. However, this side you are having what? You are having 1. So which means this is our first problem that we have. So we're just going to make a dot here to take note of it. And then now, secondly, now if we can check our carbon. Now, if you can check your carbon, you have 1 this side, you have 1 this other side. So which means now what we are having here, it is going to be what? The carbons are equal on either your reactants and your product sides. And the next thing that you're going to look at now, we are going to look at your oxygen. Now, look, you are having 3 atoms of oxygen this side. This side, you're having what? You're having 2 plus this one, which means now actually it is 3 this side, and is also 3 this side. So this is going to be balanced. Now let's check what else are we having. Now, if you can check on this other side now, if you can check your hydrogen, you're having 1 here, while you're having 2 here. So which means, again, we are having a problem here. So this is our next problem. And if you can check, it is your Na Cl. Well, yes, the Cl and the Cl are equal, right? But they are associated with some things that are not equal. So therefore, both of them, they are also going to catch the smoke, which means they are going to also be affected. Now let's see. Now what we had this side, now you had 2 hydrogen while we are having what this side while we are having 1 hydrogen. So look, now if we can insert a 2 here. Now, if you're having, you are inserting a 2, so you're going to have 2 hydrogen and you're going to have now 2 hydrogen this side. So, which means now our hydrogens now are covered. Now, let's look at something else. Now, the Cl, you are having 2 Cl, you're having 1 Cl on this side. But you are having 2 Na this side, and you are having how many? You are having 1 Na this side. So, if, let's say you can write a 2 here, right? Now, what is it that you're going to have? Look, now you're going to have 2 sodium atoms, and this side you're going to have 2 sodium atoms, which means these are going to be also now balanced. Similarly, now, if you can check your chlorine is going to be now 2 atoms of chlorine, and this side again you're having 2 atoms of chlorine. So therefore, this equation of ours is going to be balanced. How to get? Then now this is how we are going to balance it. Now let's look at now our 6.1.3 and check in terms of what is it that they require us to calculate them. Now they want us to calculate the mass of your sodium carbonate that reacted. So now let's go back to the equation, or rather the question, and try and understand it. So now from here, what are we having? Now they are saying a learner added 1,5 of sodium carbonate. So this is going to be before. So this is going to be before. So this mass here, your mass, which is your M, it is going to be your mass before, right? Now let's see. To your hydrochloric acid, now a volume of of 306 centimeter cube of what? Of your carbon dioxide gas, right? Was formed and collected under standard pressure at room temperature. Now, as soon as we see the word standard pressure, now, I think by now you are going to think of a formula that is going to have the courtesy of your standard pressure at room temperature. And remember, you're already given that this is going to be at molar volume, which is going to be your 4,45 decimeter cubed. Now, the only formula that we have that going to cater for this, you are going to have firstly your N, which is going to be equals to V over your Vm. Now, however, now what is this going to help us? Look, you are given that you have carbon dioxide, you have the volume of a carbon dioxide, and you have that also the molar volume at room temperature, it is 24,45. So which means now we can then start here. We can use this formula because this is the only formula that caters for our STP, right? So now this is going to be what? Now we can use this formula to calculate what? Now, but when we use this formula, what are we going to calculate? We are only going to calculate the moles of what? Your moles of your CO2, because that's what you are given here, your mole of your CO2, right? Now, if you are calculating your mole of your CO2, what is the volume? Remember, we said volume, it is measured in what? In decimeters. So here we are given in centimeters. So how do we move then from decimeter to centimeter? This is what you're going to do. Look, this is going to be same as your 306 over what? Over 1,000. And when you calculate this, what is going to give this is going to be 0,06 what? Decimeter cubed. So which means the first thing that you are going to do now, we are going to punch in here. This is going to be 0,306 over what? Now the molar volume you are already given that this is 24,45. Right, this is 24,45. So which means now the moles of your CO2, which is the only thing that you are given here that can at least lead you somewhere. Now, what is going to be the mole of that? Now, the mole that you are going to get of this one for your CO2 is going to be 0,012 0.25 mole. And please ensure that every time whenever you calculate something, you write the units because they are of the greatest importance. Now, we only have the mole of your CO2, right? You have your mole of your CO2. However, in stoichiometry, now, another critical aspect is whenever you have a balanced reaction, right? Whenever you have this your balanced reaction, what does it mean? So basically, a balanced reaction can help us to get something. So this was our balanced reaction. Let me just underline here. This is our balanced reaction. So from a balanced reaction, one thing that you can get is that now the ratio of everything within a balanced reaction can help you to get the mole of anything within a balanced reaction. I know this doesn't make sense, but for example, let me say, now if let's say you have your mole of your CO2 in this case, which is your carbon dioxide, you can use your mole of your CO2 to find any mole of all these things that are within the that are within this balance reaction. The only key thing that you need to do, the only key is you need to have your the ratio, right? So which means now what is it that you are going to do? Now we are going to represent this thing. We are going to see, we are going to say now, look, if we can look at your CO2, and then we compare it to the ratio of your sodium carbonate, which is the one that you are looking for, of your sodium carbonate. Now, what is it? Now, the ratio here, look, from our balance reaction here, let me write with a highlighter. You can see it is 1 here. The ratio of your carbon dioxide, it is 1, while the ratio of your sodium carbonate, it is 1. So which means if the ratio is 1 is to 1, what does this mean? This basically means now also when you want to calculate the moles, the mole of your carbon dioxide, they are going to be the same as your mole of your of your sodium carbonate. So which means now since you had these as your 0, 0,1 0,0125. This is going to be the same mole, which is also going to be 0,0125, which means even the moles of your sodium carbonate is going to be 0,125. And now, as soon as you have now understood this concept of a mole, now you can come back and say, look, you were given in terms of what is the mole of your sodium carbonate. So now you can come back and say, how can I then calculate my mass? So for me to calculate my mass, we know that mass is going to be calculated by what? Now we are going to use the formula of N is equals to mass over your molar mass, right? Now let's see. Now, because we are looking for what this is for your sodium carbonate, right? This is for your sodium carbonate. So what does this mean now? Now we already have the mole. So you're going to come back here and say, look, now the mass of my sodium carbonate, sodium carbonate in this case, it is going to be equals to what? It is going to be, what is the mole that you are given there? It is 0,0125 multiplied by, now you are going to find what is the molar mass of sodium carbonate. What is the molar mass of your sodium carbonate? Now, if you can calculate your molar mass of your sodium carbonate, you know that you are going to get an answer of what? It is going to be 100, and I think this is going to be 100 and what? 106. This is going to be 106 grams per mole, right? This is going to be 106 grams per mole, right? So if that's the case, so therefore, which means now you're going to say this is going to be the 0,125 is going to be multiplied by 106. So which means now your mass of your sodium carbonate, it is going to be equal to what? Your mass of your sodium carbonate, what you're going to get here, let's see. If you plug in our calculator, let's see when we plug in our calculator, it is going to be 1,33 grams. It's going to be 1,33 grams, right? Now, however, let's see, then this is basically going to be our answer, because now this is going to be the grams that is going to react. And this makes sense. Look, now what you were given as mass, it was what? It was 1,5. And the only one that reacted, it is only what? 1,33 grams, which means indeed this makes sense, right? Now let's see in terms of what can we do now in our 6.1.4. 0.4. Now, hopefully you've copied some of these answers in your classwork book so that you can always refer. Now, in this one, look, they want you to calculate the percentage of sodium carbonate in excess. So now they are saying, now what percentage of sodium carbonate is going to be in excess after you have used? Remember, you have already used the mass. We already calculated that it was 1, what? I think it was 1,33 grams, right? So which means from this 1,5 you've used now the 1,33. Now we want to know in terms of now from 1,5 to 1,33, what percentage? Now, what mass is going to be used in terms of percentage, right? So we are going to now do the percentage of this. Now we are going to say, now look, so what is going to be the percentage of sodium, or rather of sodium carbonate? They are looking for sodium carbonate. So the percentage of this one is going to be what now? Your percentage here is going to be your CO3. Now, what is it that you're going to have? Now, the percentage here, look, I say I'm making a mistake here. This is not calcium carbonate, but this is sodium. So, and your sodium, it's Na. Now, for you to calculate the sodium carbonates that have not reacted, unreacted, right? If there's something like that. Now, look, already you know how many you have 1,5 of the mass that was given at the beginning of the reaction. And you know that only 1,33 mass that have reacted. Now you're going to take this thing and divide with the totality with 1,5, because that is going to be the mass that you were given at the beginning. And then you multiply this by 100, and let's see in terms of what are we then going to get. So which means the percentage that did not react, it's going to be 11.33%, right? So this is going to be 11.33%. So this is going to the percentage of the mass that haven't reacted, right? So this is going to be how you calculate that. Now let's swiftly now continue to our 6.2. This is going to be yes, this is correct. Now let's look at 6.2. Now in 6.2, they say zinc reacts with sulfuric acid according to the reaction. Now the mass of zinc is recorded during the experiment and is shown in the graph below. Now the reaction stopped after 2 minutes. Now the first question, they say, now what is the limiting reagent? Now let me start by giving you a brief recap of what is a limiting reagent. Basically, a limiting reagent, when you are having your reaction, now let's say you are reacting hydrogen plus your oxygen, you are getting your H2O, right? Now within this particular reaction, now if let's say now you are in a position that you can no longer produce your H2O because either your hydrogen or your oxygen ran out first, right? Or it was depleted. So now we are going to say the one that is going to be easily depleted, or the one that is going to be, it's going to be used up firstly, right? So we are saying the one that is going to be used up firstly in a reaction, it is going to be regarded as what? It is going to be regarded as a what? As the limiting reagent, right? It's going to be regarded as a limiting reagent because it is the one that stops the reaction for it to continue, right? Now, then let's come back to this one. Look, they are saying what reacted before, it was the mass of zinc. It was recorded. They were saying zinc reacted with sulfuric acid. But look, when they are recording now here, they are only having the mass of zinc and not the mass of your sulfuric acid. So this can only mean one thing. It means now your sulfuric acid ran out first. So your sulfuric acid is the one that ran out first within this particular reaction. So this is the one that is stopping us. This is the one that is stopping us to continue with this reaction. Now let's look at now the last question, which is 6.2.2. Now in this one, now let's see. Now the question require you to calculate the initial concentration of your sulfuric acid if 50 centimeter of your acid was used. Now let's see in terms of what can we do to calculate this. Now we are going to start here. I think now one thing that you need to take note, especially with your stoichiometry, one of the key aspects of it is having your reaction and is having your balanced reaction, because it can help you with several aspects of things. Now let's start here. So what is it that we are going to do now here? So look, we are only given the mass of what? We are only given the mass of zinc, right? And we are also the only thing that we know about the sulfuric acid is its volume. So which means the only thing that we have at least maximum information of, it is your zinc. So we are going to start with the zinc now. Look, if we can calculate what are the moles of zinc, we can then take the zinc and say now zinc and your H2SO4. Now compare their ratio, and after we've compared their ratio, then we can conclude, or rather we can get what are going to be the mole of your sulfuric acid, right? You get it now, isn't it so? Yes, I can see you nodding there, which means you are getting it. Now look, let's start here though. Now we need to start by calculating now what is going to be the mass of our zinc, because we are not given a precise mass. Now look, the reaction started, it was 5, but now it ended, now it is 2. So which means now the total mass that was used there, it's going to be 5 subtract 2, which is going to be what? Which is going to be 3 grams. That's where we are going to start. Now, secondly, now we are going to come back and say, look, for moles of your zinc, it can be given by what? By M over your what? Your molar mass. Now, what is it that we are going to have now here? Now, this, look, you are having 3 grams of your zinc that is going to be used in this reaction. And the molar mass of zinc, I think we all know that this is 65. So now, then let's write it in here. So therefore, which means what is it that you are going to have now here as your moles? So which means your moles of your zinc, they are going to be what? It is going to be 0,0462 mole, right? So this is going to be your mole of your zinc. Now that you have calculated the mole of your zinc, you will come back and say, look, now I have a balanced reaction. I have my reaction here. Now, let me now compare the ratio, right? Let me compare the ratio of these two things. Now, look, we are going to say now the zinc is to the ratio of what? Of your H2SO4, which is your sulfuric acid. Now, their ratios, they are 1:1. So what does this mean? This, it can only mean one and only one thing, right? It simply means now, if you are having 0,0462 moles here, the same thing here, you are going to have 0,0462 moles also of your H2SO4. Now you are at least halfway to solve this. And now that you have the moles, now you can start and continue. Because look, you are given now for the sulfuric acid, you are given the volume, right? And they want you to calculate concentration. And you know the formula for concentration, it is your N over your V. Now we can then come and calculate what is going to be your concentration of your H2SO4. Now, what is going to be that? Now, what is the moles first? Now, the mole of your H2SO4, we've already calculated. It is 0, what? 0, 0,0462 over what is going to be now the what? What is going to be the volume? The volume, remember that because this is in what? Can you see that this is going to be in centimeters? So this is going to be 50 divided by 1,000. So this is going to be 0, 0,05 what? Decimeter cubed. Then you come here 0, 0,05 decimeter cubed, right? Decimeter cubed. So therefore, which means the concentration of your H2SO4, you see now, I think you are getting it from your calculator the same way as I am in this one. It is 0, 0,92 moles per decimeter cube. Please don't forget that every time, whenever you're calculating concentration, it is measured in what? In moles per decimeter cube. So please do not make the mistake of not writing the units. So basically now this is how you are going to, deal with this type of questions. And I think this is going to be as far as our questions. So they end here. Thank you very much.